Alright, let's do the second lecture for the sub PChem. In this particular lecture, I am actually going to talk about the basic thermodynamics. And the study of the thermodynamics is originally developed to study the steam engines. Nowadays, it's actually covering a lot more stuff, so that it becomes more and more important. Especially if you're talking about are going to be interested in the process of what's happening in our body, then you need to understand the thermodynamics pretty well. So for this particular sections, we're gonna learn the energy transfer. Could be the heat transfer, or could be the work done by the system or done on the system. So it's the work and heat. Those are the two energy transfers. And the stuff that we talk about the work, we are going to talk about the expansion work only, which is actually used fairly often in engineering, but not very common in the biochem. The biochem actually is more or less the study of the non-expansion work. That's the truth to the biochem, and it's covered in the later part of this class. So we're not ready to actually talk about any of those stuff. So we're going to come back to the non-expansion work later. Alright, definitions is very important in the science. So you're going to actually define the thermodynamic keyword in this particular lecture. The system is the stuff that you're looking at. So for example, if I'm looking at this cup right here, then that's the system. Everything else is the surrounding. If I'm actually interested in the what's in the pot, then that's the system. Everything else is the surroundings. I hope you got that. System and surroundings. Okay, let's start out with the first law of thermodynamics. The first law of thermodynamics in English, the plain English, is pretty much says the energy conservation. Energy can't be created or destroyed. So basically that portion right here, the energy conservation, right? That actually sets up interesting equations, because if you can't actually create or destroy the energies, then you can transfer energies, right, in and out. But that can happen in only two ways. It's either work or the heat. Those are the only two ways of transferring the energies. Then whenever the system changes the energies, then the changing energy has to be either comes from the transfer of the energies in two different kinds, work and heat, right? Because you can't really create or destroy the energies. So that right there is actually the first law. The first law of thermodynamics is the changing internal energies, or the changing energy of the system, is equal to the work and heat. Both work and heat is the energy transfer. That's the only two ways that you can actually transfer energies. Okay, right? Then let's dive in a little bit more about the work and heat. So the work is done to achieve the motion against an opposing force. So most of the time that we are going to be actually dealing with the pressure, because pressure is actually, by definition, it's a force by area, right? Force divided by area, or the force per unit areas. So the force and pressure is pretty much proportional, given that contact area is constant, which is usually the case. So if the work is done against the force, then that opposing force, then that's against the pressure. The heat is the energy transfer, and that energy transfer that happens from the high temperature to low temperature. So if the two objects are having a contact, and the heat, I already know that heat is actually traveling from the high temperature to low temperature. That's always the case. The heat never travels from the low temperature to high temperature. It's high temperature to low temperature. I'm going to actually talk about why that's the case in the next couple of slides. Not the next one, but maybe next few slides. So the transfer of energy, the first type, is a work, and then you probably remember that work is actually equal to negative external pressure multiplied by the change in volume, right? I hope that you do remember that from the general chemistry. Now, let's just think about one particular example here. So you have a system is closed by lid right here, and then it has the weight on top of it, right? And then the system is trying to push that lid upward, right? So now that the lid moved from here to here, the definition of the work is, this is from the physics, right? That the work is equal to the force multiplied by the distance, right? That's the definition of the work. This is coming from the physics 1 probably. But force is related to the pressure by these equations right here. So force is actually equal to pressure multiplied by the area, right? So I'm going to replace this force right here by the external pressure multiplied by the area, and then distance stays the same right here. So for this particular picture right here, you have this area, and then this is the distance it traveled, right? So what is this? So you have area that multiplied by the distance. That's a change in volume, right? So these guys are actually replaced by the delta V right here. So you're getting this Px external, the external pressure multiplied by the volume, a change in volume. You got that one. And I have to actually work on this sign conventions right here. In this particular case, expansion, the system is working hard to actually push this lid upward, right? And that energy actually has to come from somewhere, right? Where does that energy actually come from? It actually comes from the system itself. So system spent some energy to push the lid upward, right? Does that mean that that system energy is decreased? Yes, it is. So the expansion work has the sign of negative. So anytime that you're dealing with the expansion, the sign convention is going to be negative. And anytime that the system is compressed, then that energy the sign associated with the work is going to be positive. In other words, that energy is stored into the system. So work done on the system means that the system is actually gaining the energies, and work done by the system is actually losing the energies. Okay. I should probably mention one thing. If what do you think about the external pressure is 0? If that's the case, then work is actually equal to 0, because 0 multiplied by anything, regardless of the sign, is going to be 0. So the free expansion literally means it's free of cost, right? Alright, transfer of energy number 2, which is the heat. Heat is always transferred from the high temperature to low temperature, and whenever I think about the heat, heat is always associated with the randomized motions or the unorganized motions, and unorganized motions are very difficult to use it. So for example, like in a walk, everything is moving in one direction. I forgot to actually talk about this one, but the walk is actually, for this particular case, the lid is moving upward, right? And that atoms or the molecules in the lid is actually all moving upward, right? All of these guys are moving in a uniform motions. Those are very useful, because if the car, every molecule in the car is moving uniformly, then you can actually step on it, and then you can actually travel to somewhere, right? So walk is really useful, but the heat is actually going all over the place. It's a randomized motion, so it's an unorganized motion. So you can't really use the heat as much as the walk. So engineering point of view, you wanna avoid the creation of you wanna avoid the heat as much as possible. You wanna create more work, or you wanna do the transfer of energies by work, not the heat, right? So there are 3 types of heat transfer. One is the radiations, and the radiations, a good example is the sun right here. So you have the sun right here, and then some planet like the Earth and Moon is actually getting the heat from the sun by the radiations. Radiation, for this particular case, the sun is emitting photons. High energy photons, and then those photons are absorbed by the molecule in the atmosphere, and then those atmosphere is actually getting the energies from absorbing some of the photons and heat up the entire planet. The convection is just like a convection oven, right? It's maybe I should probably stuck with this particular example. At the bottom of the pot, it's touching the hot plate right here, so that the liquid is getting warm compared to the top of the liquid, right? So hot water is going to just move around to actually heat up the entire body of the water. So basically that heat is actually transferring like this, like many times. It's moving all over the place. Those are actually convections. Convections relate to something that's moving. The conduction, on the other hand, is actually the molecule itself is actually not moving. So for example, on average, so around here, you have this handle, right? And if you keep the pot on the hot plate for very long time, any of the molecules somewhere around here is actually moving in all directions, going up and down and up and down, and then they're going side to side, right? Intensely, because it's hot. But these hot moving molecules, or the atoms, on average it's the same spot, but moving very intensely, and that molecule actually induces the motion on the next molecule right here, because these guys are moving all over the place. These guys start to move more rigorously or vigorously than before, right? And then all of those guys induce another molecule that's moving slowly initially, but as you heat up the pot for very long time, then all of those molecules just induce the next one to move a little bit more vigorously, right? And then those are actually the conductions. Conduction, on average, the molecule doesn't move, but it induces the motion to the surroundings. Those are conductions. Conduction and convections. Those are slightly different. So let's think about the sign conventions. That's wrong. Conventions. Okay, good. Alright, so let's just say that that system is a gas, and then we actually put the hot plate from the left. And all of these hot plate actually contains a molecule inside of this hot plate that's moving super fast, left to right, right? And then the gas molecule that's hitting this wall, the hot wall, as soon as it touches the wall, it will bounce back very fast, because the hot wall right here, all those molecules in the hot wall is actually making the gas to actually move even faster. So in this particular case, before you actually apply the hot plate here, the gas molecule are moving very slowly on average, but by putting the hot plate on one side, the gas molecule, all the gas molecules actually speed up, right, more vigorously. So any motion of these molecules actually intensified, right, in this particular system right here. So for this particular case, system is actually gaining more energies. So for this particular case, the system is like the heat gained by the system is actually positive right here. Now let's think about the cold wall right here. The cold wall did not move as much as the hot plate right here. Then what's going to happen to the gas? The gas initially moving at 300 meters per second or so. As soon as it hit the wall right here, some of those energies are actually stored in this cold plate, right? Sort of like you're jumping into the pool of balls that as you jump in, that some of those energies are actually dissipated into the balls, or maybe that for this particular case the molecules in the cold walls. So as soon as the gas molecule actually hit the cold wall, it bounces back much slower, because it loses some of the energies, because energy is transferred to the cold wall, right? So after several minutes, by actually putting the cold wall right next to the system, the energy is actually absorbed by the wall, and system lost the energies because you see that all these molecules, the gas molecules, are moving slower, right? So I'm actually using these things as kinetic energies because the ideal gas doesn't interact at all. 1/2 mv squared. That's pretty much all I have. So that the faster they move, the energy is higher. The slower they move, energy is lower, right? So if you put the hot plate, energy goes up, system energy goes up, and then if you put the cold plate, energy is going down because the speed of the gas is going down, right? So for this particular case, the sign convention is going to be negative for this one right here. Okay. Then I think you probably have seen this one in the general chemistry too. The open system, the stuff can go in and out. Some molecules and stuff, right? Can go in and out. Of course, that heat can go in and out. Those are open system. The closed system, now that the molecule cannot escape, but heat can go in and out, or the energy can go in and out. Those are the closed system. And then isolated system, the stuff cannot go, the molecule cannot go in and out, and then also the energy cannot go in and out. Those are isolated system. So let me just clarify what's going on. What's in this pot right here is a system. This is open. And then maybe this is closed. Lid is closed. Maybe maybe this one. This is closed. The molecule cannot go in and out, but the heat can go in and out, right? Now if I put this right here, then the system is isolated because heat cannot go in and out here. And these, by the way, this is going to be sort of like a side stories, but if you see the inside of this summer mug here, they're usually a shiny surface, right? And the shiny surface, there is a reason for that. Let's just say that you have a hot stuff here, right? Then that hot stuff is going to emit the heat by radiations, right? And that radiation can be absorbed by the black surface inside of this cup right here, right? Then those heat is actually transferred from the liquid to the wall. That's not good, right? So they actually put the shiny reflective surface so that if the heat actually, the system actually radiate the stuff from the system, then it bounce back because it's reflective. So there is no heat loss with the radiations. And then usually on these thermal mugs, they have a vacuum wall inside, and that reduces the conduction, right? Because there is nothing that you can actually conduct the heat escaping from the system to the outside, right? So the vacuum wall is kind of important. And then that convection, the heat is actually going, and actually the system is actually maybe circulating inside slightly, but as long as you don't lose the heat from somewhere, then probably that it's not going to circulate that much, right? So that it cuts off all three different heat transfers. So these thermal mugs are fairly good design from my point of view. Oh, another stuff. The definition of another definition that you probably need to remember. Diathermic allows the heat transfer. Adiabatic, the heat is not going to transfer from in and out. So anytime that you do the calorimetry experiment, you use a styrofoam cup, right? And because the styrofoam cup does not transfer the heat from the inside to the outside, so those are adiabatic. Okay, so I think this is probably a good enough point to actually work on some simple problem. So let's do this one. You can probably pause the video right now and then you can probably solve this one. So let's just pause the video. You do this one. You do this problem right here. Alright, so you probably solved this problem already. So let me just go over some important steps right here. So we are considering the reaction which increases the number of mole of gas by 1 mole, right? And that 1 mole of gas, the formation of the extra 1 mole of gas at 1 atm probably is close to 25 liters. So we assume that it probably increase the volume by 25 liters. Then another stuff is that the external pressure is 100 kilopascal. 100 kilopascal by the pascal is a SI unit, right? The SI unit use meter, kilogram, and second. Those are the unit that they use for the pascal right here. I'm not saying that multiplication of the meter, kilogram, second, but the pascal can be expressed in terms of the meter, kilogram, second. So these are SI unit, right? So whenever we are dealing with a volume change of the 25 liters, more precisely it's a 22.4 liters, we're going to change that, we're going to have to change that to the meter cube. So the 1 liter right here is 0.001 meter cube, so 25 liter is approximately 0.025 meter cube. And then we have this 100 kilopascal multiplied by 0.025 meter cube. Now another hint right here is a pascal meter cube is a 1 joule. So this and that is going to make a joule. So it's going to be a kilojoule, which is going to be 0.1212. So it's a 2.5 kilojoule. So 2.5 joule was 2.5 kilojoule was 2500 joule is the answer to this problem. Now we're getting finally to the isothermal reversible process, which is very important for the study of the thermodynamics. So the isothermal means that the temperature stays constant. And what's reversible process? The reversible process, from my point of view, is any process that is occurring very, very slowly. So for example, if I actually, let's just think about the system as the air right here, right? And then I open the door very slowly. open the door very slowly and close it. All of this motion of the door is actually very slow, right? So compared to the gas that's moving on average of the 300 meters per second, my door is actually moving so slow that it doesn't really disturb the motion of this air right here. Right? Those are, generally speaking, it's a reversible process. It's so slow that it doesn't really cause much of a disturbance on the systems. Those are systems or surroundings. Those are reversible process. Then what's irreversible process? Irreversible process is that it actually causes a disturbance. For example, if I actually open the door at faster than the speed of the sound, like 300 meters per second, right? And then close the door by 300 meters per second. Each time I do it, right? If I can actually move the door by 300 meters per second, then I will create a shock wave, right? And that shock wave actually disturbs the motion of the air. It actually mixes up the things more, and it actually causes great deal of mixing, and that's irreversible process. Another way to actually think about it, it's probably more intuitive, is that if you have the cell phone right here, and then on the smooth surface, I move this sheet of paper going from here to here on the fairly frictionless surface. Then, because it's a frictionless surface, I'm not heating up the molecule at the surface of this phone right here, right? Those are reversible process, because any of the motion of the molecule right here at the surface is not disturbed by me moving this sheet of paper, right? But if I'm actually moving this sheet of paper with the rough surface like this, right? Then what am I doing here? I'm actually heating up the surface here, right? Because if you actually heat up, try to rub your skin with the sheet of paper very hard, then your skin is gonna heat up, right? The same thing here, that if you have a rough surface, then many of the molecules at the surface is gonna start moving fast, or maybe jiggling fast, or more intensely jiggle, right? Now that any of the molecule here is actually moving in random directions, going up and down or the side to side more vigorously than before, right? Those are irreversible process. So any of the friction makes the process irreversible, because you're introducing the unorganized motions. Unorganized motion is very difficult to make it useful. Any of the organized motion is easier to use it, but unorganized motion is very difficult. I will post this slide to the blackboard. So what I want you to do is actually look at this particular slide and then read it and then try to understand what's going on. If you have any questions on this particular slide, ask me questions on a Discord. Alright, so let's do the isothermal reversible process in terms of the equations. So we're talking about the ideal gas. So we are going to use the PV equal nRT, and then the definition of the work is the negative external pressure multiplied by the volume, right? But P right here, from this, right? P is actually nRT over volume, right? So we can substitute this external pressure by this, right? And then work right here is actually a correction of the small volume change, right? So it's integrations right here. Now that nRT is going to go in front because the only variable right here is the volume right here, right? So everything else is just going to go in front. So you actually get this right here. Now if you use the integration table, then that integration is actually the log of volume, right? And then that log of volume BF minus log of volume initial, right? So minus sign right here, it's gonna make the volume initial volume at the bottom. So for this one right here is actually equal to minus nRT of the ln of the BF over BI right here. But because of the negative sign always put the numerator to the denominators. So the whole thing is going to flip. You get nRT log of BI over BF. So work is actually equal to this one for the isothermal reversible process. So what does that mean? That it's as the volume changes, the external pressure changes accordingly each and every step of the way. Now you should probably check to find out the sign of W when it's in expansion or the contractions. So let's just think about that one. So log of the expansion, small volume divided by large volume, right? That's the expansion, right? Then for this particular case, that the log of less than 1, right? Which means that the work is going to be negative. So anytime that you expand the isothermal reversible process, which is going to lose the energies. Now, if I'm actually going just around contractions, then the initial volume is going to be large. The initial volume is going to be large, and then the final volume is going to be small, right? Then this is bigger than 1, which is going to be positive, right? So the work is going to be positive for this particular case, which is all consistent. So now the final sort of this reversible isothermal reversible expansion is that what's the work compared to the work against the constant pressure. So from the beginning to the end, we have one external pressure, constant external pressure. Remember that the integration is area under the curve, right? So if it's the constant pressure, then area under the curve is very small, right? Let's make these things to the two-step process. Then initially on up to the half point, you have this one pressure, right? And then from that point on, you have a reduced pressure right here. Area under the curve is that portion, and that portion still small compared to the actual integrations, right? This is large, and that large process, because you're going with every single step super slow, thus it fills up all the way up to this line right here, right? In this particular case, area under the curve is maximum. That means that the reversible process, isothermal reversible process, is actually the maximum work. Right, this is good enough.